Along with Anderson Verber and Grace Gregory have organised this meeting. We're very grateful indeed for Anderson stepping in to fill a huge void left by incapacities in both Nikki and myself. But welcome one and all to the meeting. What I'd like to do is, because there are some new faces, I think just very quickly just go around the room with the name, so we can make sure that everyone's at least got a name and a face. Greville Kroll.
Tony Deakin.
A founder.
I was, no, not a founder. I go back to the fourth meeting, I think.
Fourth.
Yes.
Well, welcome, Tony. We're just going to do a very quick walk, so everyone's got a name. So,
Michael Heather. Nick Rossiter.
Roger Anderton.
And Paul Mountcastle.
Dino Zetti.
Richard Amoroso.
Geoffrey Constable. I go back almost as far as Tony, but with much less distinction.
Geoffrey Constable.
Luke Rothman.
Luke Ellsbury. Graham Ellsbury. Nikki
Grace. Diane Sladiero.
Ron Wheaton.
Ron Wheaton.
Yep.
Tony Booth.
Tony Booth.
I'm Stephen Fry.
Stephen Fry. Anderson Verber.
I'm Garnet.
Okay, so, these to work. There's going to be time for your presentation on it. There we go. So, Garnet's going to talk to us on the superposition principle and binary images in space-time. We're about 15 minutes late, so just we'll delay the proceedings like 15 minutes. Perhaps just allow a little bit of time at the end for questions. Sure. Thanks, Garnet.
Well, it's great to be here. Great to see these familiar faces. And I would like to thank Nikki, Grenville, and Anton, who've done a great job keeping this group together. So, I wanted to talk about the superposition principle, really. That's the basis of what I'm going to be looking at. The images, we'll sort of see them as we go by. So the issue here is this, old icon of quantum mechanics. If you think of the double slit experiment, then think of sending electrons through two slits. If they were particles in the classical sense, you'd expect that with one slit open, you get one or the other of these two things. And there's a superposition principle for that, which would just say, well, okay, if we have both slits open, we would just add them together, and we get a distribution that would look like the sum of these two things. But in actual fact, when we do the experiment, of course, we know that's not what happens. If assuming we get the scale right, what happens is that we get a diffraction pattern where there's interference, and so you have this peculiar effect that if you start with one slit open, you open the second slit, and when you open the second slit, the intensity diminishes. So, one sort of, in a way, the mathematics is straightforward, but figuring out where it came from is not quite so easy. So, what we want to do is try and figure out what the origin of the superposition principle, and what is it that really breaks this classical superposition, which would just say, look at the probability densities, add them together, and you should get a simple pattern. And so there are, in a sense, there are two central questions. So, if electrons can always be directly observed as particles, suggesting probability density functions, representing them, what is the phase of the wave function? I mean, we know we use the wave function in the Schrödinger equation. Where does the phase come from? Why is it there? And assuming we can find the phase emerging from a physical argument, then what underlies the superposition principle? So that's where we're going, and I'm going to try and convince you that in actual fact, you can get to where we want to go, and you can answer those two questions with pretty simple special relativity. That's the That's the interesting thing. Now, of course, the square root of minus 1 comes into this, you know, where did the I come from? And we can see that you can get from a classical picture to a quantum picture simply by introducing the unit imaginary. So in this second column here are the classical equations. And so at the top you've got the diffusion equation, you just throw in the square root of minus 1, and you've got the Schrodinger equation, and you know, we've got these pairs. So telegraph versus the Klein-Gordon. Again, you just introduce the square root of minus 1. Telegraph and Dirac in 1 plus 1 dimensions. Classical versus quantum mechanical. And the point here is all of these classical equations we understand from a more basic theory, right? There's a statistical mechanics underneath these two that tells us why we have these equations. And there's a superposition principle involved in both of these. One is for PDFs here, the probability density functions, and the other in the quantum system is for the wave functions. And it's really that we really want to get at. So in terms of the popular term emergence, we know where these guys emerge from. We know there's an underlying stat mech that gives you the classical equations. We don't really know what underlines the wave function in quantum mechanics. So what I'm going to try and convince you, and in the end it's going to be a very, very simple argument, but the phase of the wave functions are a manifestation of relativistic time dilation. And that the superposition principle, all it does in actual fact, it moves paths that can conflict with special relativity. So that's the argument I'm going to run by you. So the model is actually very, very simple. The model is to say, let's back off from the world line concept in special relativity and say, let's make this discrete. And think about events equally spaced in time that form a clock. So we're going to, in actual fact, replace the world line by a clock sequence. So what we're really doing is we're transporting what is in special relativity pushed out to space-time. We're pulling it back and saying there's actually a signal associated with every particle. It's binary, and it acts as a clock. So the binary aspect is represented here by two different colors. The binary thing is it's the minimum. It's the minimum amount of information that you need to form a clock, right? If you've got tick-tock, you always need the two things. You can't get away with one, you need two. You have one, it's just a constant, you have nothing to compare it to. And in special relativity, the idea of a world line has no clock associated with it, right? It's just a beginning and an end, and the particle itself, there's no time encoding actually in the world line. And that's the one thing we're going to amend. And we amend it by stepping back out to a discrete case and saying, okay, well, that associated with every particle, there is a clock that runs at the Compton frequency. And we're going to say it's a binary discrimination. We're going to be able to detect this just through a binary yes/no. Is it there or isn't it? And so with this, you can see that that's well. So think of these areas as two different colors of the tick and top of the clock. We're just going to associate plus and minus 1 with the two things. It's just a single bit of information. Usually you go 0 and 1. Here we're going to go minus 1 and 1. We'll see in the algebra actually why we do this and what happens. Okay, so just going back to this thing. Here's in its rest frame. Here's a boost. So let's look at the ensemble of clocks from different reference frames. When we do that, you get the rather familiar looking pattern. So this is just a single. You take the single clock and look at it at all velocities. So time is going in that direction. And if we fix the time and look along space, along here, well, this is what the pattern looks like. Okay? And so in actual fact, it's a mapping onto space of the age of the clock. So this guy here is the last cycle down here, right? Last half cycle. There's the second last half cycle. There's the previous cycle. So as you go back along, as you go out along the x-axis, you're just seeing the clock earlier in time. So if you see that pattern, some of you may look at it and go, oh, that looks rather familiar. Well, okay, so this is just saying what I said, which is that pattern is the history of the clock. And it's a single clock that you've just looked at in different reference frames. So there's that pattern. I guess that unfortunately the colouring has gone on this thing, so you can't really see. But so the pattern you saw, here's the top, straight down, back up again. So it's a square wave of different frequencies. That's the pattern we just saw. This thing in here, that's just the real part of the Feynman propagator, the non-relativistic propagator. And the thing to notice about that is, well, okay, this relativistic binary clock, it knows about the propagator. Yeah?
You mean the Feynman propagator for the Dirac equation or for the Schrödinger?
For the Schrödinger equation. Because this is,
So you're saying that the Schrödinger equation, even though ostensibly doesn't look like it knows about relativity, doesn't?
Absolutely. Absolutely. This is where we're going, and that's what I'm going to try and convince all of you is the case. So this thing here, this guy here, is special relativity alone. There's no quantum mechanics in it, right? But when you look at it, you can see, well, okay, the sign of this thing is the same as the sign of the propagator. The transitions are the same at the same point. It's in a sense a discrete version of the Feynman propagator. Okay. If you took this out further out, this is low velocity, and the reason it works for the Schrödinger equation is this is low velocity. As we go farther out here, they disagree, but then that's because the Schrödinger propagator is incorrect. So yeah, so the sign of the binary clock and the propagator are the same. The discrete phase of the binary clock is special relativity. There's no quantum mechanics in this. So have a look at the square. So the square of the binary clock propagator, notice what's going to happen. It's just going to flip this thing up and just give you the constant function. Okay, so when you take the square of this, what I'm calling a propagator, I haven't shown it as a propagator, but I'm calling it that anyway. So there, it's just this constant function. The square of the real part of the Feynman propagator is this thing, but of course you know that when you put in the imaginary part, it fills that in. So if uxt is the binary density, then u squared xt over 2t is uniform. This factor in here, the 2t, just comes from the light cone. If c is equal to 1, you look at the light cone, and the width, particularly of t, is just 2t. So if you look at this thing, it's uniform PDF. So if you integrate through it from minus t plus t, you get 1. So it is. We can think of it as a probability density function, which just said, if you interpreted that, it just means that all velocities are infinite. And so, of course, compared to psi star it's uniform. So just let's compare these two objects. So we're thinking of this thing as the propagator. So there's the usual free particle propagator from quantum mechanics. And what we've got is just this guy on the right. What are these things? Well, if you take their square, in actual fact, the modulus of this thing, you get this, which is a relative probability density function. It has to be relative because for Schrödinger, it's on the whole real line as opposed to just 2t. Here it's exact because propagator is 0 outside the light cone. In terms of continuity, well, yes, the Feynman propagator is smooth. The binary clock is only piecewise smooth. And the phase is continuous for the Feynman propagator. It's binary for this relativistic clock. Superposition, well, we know we have superposition for the propagator for quantum mechanics. We don't know about this thing. Right? All we've done is we've said we've got a binary clock. we're going to let it go and look at it. So we don't know whether a superposition principle is relevant or not. As to a world line, well, no, the final property it doesn't really have a world line. It's not, you know, it's just not part of a quantum formalism. And there is the analog of a world line for the binary clock. There's the tick sequence. And so far, what we've got from these things, well, the central density for quantum mechanics is the wave function. For this thing, the only thing we can interpret directly at this point is that it looks like we've got a PDF when we square the thing. So we've got these similarities, and what we really need to do is figure out a couple of things. We need to figure out the phase. Can we make the phase continuous and make it look more like the phase in the Feynman case? But the real question mark is here, right? Even if we find the phase and say, yes, we know how the phase becomes continuous, what the heck are we going to do about superposition? What does superposition mean? So let's have a look. What we need to do in order to figure this out, we're going to set up the equivalent of a double slit experiment, because that's where we're going to see whether superposition makes sense. So we're going to invent this thing that I just call a hinge reference frame, and all it is taking inertial reference frames and flipping between them instantaneously in such a way that you don't actually see it in the clock. So let's just have a look at that. You can think of this just like the twin paradox in special relativity. So here's one of these clocks. Right? Think of that as the Earth twin. And here's a hinge frame clock. So by hinge frame, I just mean we go along and at some event, we switch to the rocket going in the other direction. So there's a huge acceleration hidden in this thing, but the clock still goes on. So the clock itself doesn't notice the acceleration because it happens at a point, and we can just sort of count the time. And when we look at this thing, we say, well, okay, we've seen this before. The hinge frame clock, we look at this thing and say, well, oh, when we look at it, it's got 4 cycles, whereas this one had, whatever it was, 5.5 cycles. That's perfectly reasonable. This is just a twin paradox, right? Here's the Earth twin, here's the rocket twin. And notice that when they meet, 2 things disagree. The first thing is the age. We expect that from the twin paradox, right? Because this guy has zoomed out at some vast velocity and come back. So he's younger than the one that stays put. But notice that for this particular case, the parity disagrees. Now, the age disparity, perfectly respectable part of special relativity. So the fact that they're different in age is not a surprise. The parity disagreement isn't actually covered in classical special relativity because world lines have no inner scale. So it's not an issue. But we've given this clock an inner scale, and we've given it a binary signal. And so it's the binary signal by which we are going to check on time. So this thing, the fact that up here, the fact that the binary phase disagrees is going to have consequences. Let's. What we really want to do is set up what we call here just a hinge-Lorentz equivalence. So here's another one of these, stationary clock, rocket clock. These guys agree at the end. And why is that? Well, the reason is at this bend, what happens is both of these are Lorentz transformations of each other, and they miss out a full cycle. Okay. So with the full cycle missing, what that means is that the rocket twin is actually an image under appropriate Lorentz transformations of this one. Okay. So if we go back, the predecessor of this is this, this is this. They map back onto the original clock. So this, in actual fact, is just an image of the original one with a full cycle missing. Okay, so once we have that, what we need to do is say, well, okay, what are we going to do about this? Well, what we really need to do is just extend the idea of an inertial equivalence. And the first relativity postulate demands the equivalence of all inertial frames. Hinge frames for clocks preserve periodicity, but cannot guarantee the same elapsed time between two events. That's fine. That's we don't expect them to be the same. But in this case, a minimal extension of equivalency would be to demand the preservation of parity between hinged paths. So they are, in actual fact, images of the same path. Okay? If they disagree at the end, they're not Lorentz images of with the same clock. So, equivalence between paths means they differ by full period deletions. And so inequivalence just means that they differ by partial period deletions. And physically, the inequivalence means that the two paths are not Lorentz transformation images of the same clock. Okay. So what we're going to do is we're going to say, okay, let's represent the ticks of the clock by plus or minus 1. Because what we want to do is we want to change the ensemble of paths so that you never get conflicting clocks, because you want all of the paths to be images of the same clock, in the sense that there has got to be one clock. There's one clock particle, right? So in the ensemble that you end up with, you want to have all of those paths be just images of the same clock. So that's the deal. So here's the binary clock double slit experiment. We just say, okay, there's a clock attached to all of these guys. And so, red, blue, red, blue, red, blue. If you come through here and say, oh, these guys don't match, then these two paths are not images of a single clock. And if they're not images of a single clock, we want to get rid of them. Oh, but then that's very convenient, because if we attach plus and minus 1 to these guys, that's exactly what that does. If these two don't match, they have a different sign, and so that path is rejected from the ensemble. And so when you look at this thing, well, as soon as you do that, it throws out this. Because this ensemble where we said, just add the PDFs from one slit to the other slit, as soon as you put this in, as soon as you put in the parity, you have to start throwing away paths that were there when you only had one slit. Okay, and it's just a binary process. So, pairs of paths through double slit are hinge inequivalent. The contribution of the paths cancel if we go with plus or minus 1, according to the tick and tock of the clock. And so here, the propagator rather than the PDF is going to add. Okay, so what does this mean? This means that in actual fact, immediately you've got non-locality. Because you put in both slits, and there are paths that are in a sense metered by the clock, and everywhere on the detection screen, you have to say, okay, the path from the detection screen to the two slits, are they Lorentz images of each other? If they're not, you throw it out. Okay, so the equivalent classes are non-local. At the detection screen, you have to have the information from both of the slits. Okay, so elimination of the inequivalent paths in the double slit experiment means that PDFs do not add. You can't use the addition of probabilities anymore because you eliminated a whole bunch of paths from the ensemble. Okay, so the superposition of binary propagators, all it does is enforces elimination of inequivalent paths, and it produces interference. And notice this interference has nothing to do with quantum mechanics. We haven't built in a formal analytic continuation. This is simply a model. We're saying that clocks have a binary phase, and they respond to special relativity. And when we send these things through a double slit apparatus, when they come together, they've got to be Lorentz images of a single clock. Okay, so here's an example of. I guess we can't get better resolution, but okay. So the color has vanished from this, but so the binary clock, here it is. It's disappeared in there. There's a bit down here. There's a bit down here. There's a bit up here, a bit down here. So this is a near field double slit experiment with a binary clock, and you can see what it does. It's yanked out bits of the spectrum simply because you've got the binary paths that are cancelled. So. Okay, so the binary counting. Let's just see how the counting goes. So here's the. So this just gives us the algebra. Here's one of the clocks, right? So we can think of this plus minus, but we're going to divide into the diverging part and the converging part. So you'll get something that's 1 here, 1 there, -1. -1, and that's a complete cycle through there. So we've just taken this and said, okay, it's binary, but we can also recognize the difference between convergence and divergence. And you could just sort of work through that. How do we represent these things? Well, this guy will represent it as a 1 and a 0. This is going to be a 0, 1, 0 minus 1, 0 minus 1 the other way through the period. So it's a four-state process. And so here's the four-state binary clock. It gives you the spiral. So the things that are real in here are these vertical segments where the clock is between ticks. It gives it a rather funny appearance. This is an instantaneous tick here. So just think of these four states of the clock. And so we just have these four states, and the obvious question is, well, how is this going to become the regular spiral of e to the I t? Well, all you actually have to do is, when you start out with this thing, you fixed the origin and you fixed the phase, so it's completely specified. But if you actually say, okay, well, let's say that you can't fix the phase precisely to begin with, and just put in a stochastic element. You put in a stochastic element and just do an average. This was average over a few hundred, this was an average over about 10,000. You can see, well, yeah, you just get the spiral that you expect. So going from the discrete to the continuous, there are a number of ways you can do it. What about the square root of minus 1? Well, again, pulling the calculation back a bit, here are four states, right? So what we're going to do is say the clock, all it does is it flips through the four states. Here's the permutation matrix that does it. So this guy is an operator. But what we want to do is we want to subtract the opposing states. So we just do a change of variables. When we do that, the evolution operator for the difference becomes this. And that's just I sigma y, and it's just a matrix version of square root of minus 1. And it moves these four states through the sequence that we expected. Okay, so here's our version of the square root of minus 1. So that thing just gives you minus the identity. All right, so the origin of superposition here. So the binary label, so choosing plus or minus 1 to be the discrimination variable between the two ticks of the clock, what that does is, when you look at the end, so if these are different, you want to get rid of these two because they're not images of each other. They're not Lorentz transformations of each other, and so they're not images of the same clock. So the plus and minus 1 just does that, right? If you have up here blue, or what comes out to be white here, white and red overlapping, you want that eliminated. So those will be opposite sign, and so they will be eliminated when you add them up. Okay, so let's note that the superposition of PDFs and preservation of the hinged equivalent are not compatible. Right? The PDF won't survive if you do this because you've changed the ensemble. It's no longer an either or through either slit. You have to say, okay, the two slits are there. Let's look at the ensemble of all possible paths, but make sure that if we keep an ensemble member, then the two clocks are images of the same clock. Okay, so superposition of the phi and preservation of hinged equivalent are compatible. So we can just add the phi as opposed to adding PDFs. Okay, consequences. Okay, so the phase of the wave function in non-relative quantum mechanics follows directly from time dilation and special relativity. So that was that first thing where we looked at the comparison of the binary clock versus the Feynman non-relativity propagator. Right? You can see from that, yes, that the phase for the Feynman propagator just comes from special relativity. So, what about the superposition principle? Well, here we see what the superposition principle does. It just removes the contribution to the propagator from paths that aren't Lorentz transformations of each other. Okay, so they're not images of a single clock. Okay, another consequence is the chessboard model, actually, which is, I think, familiar to quite a few of the people in this room. When you look at it carefully, you see all it is a model is summed over all hinged frames. But you do the stochastic simultaneously. Right? So you put in the stochastic rather than saying, I mean, this calculation, all it did is it said, keep it binary and see what happens. And then you see where the effect of the superposition principle comes from. And then after that, you put in the stochastic thing. You say, oh, well, that wipes out the binary aspect in a sense and gives you a smooth propagator. So when we look at this thing, the four states are the same, as is the binary discrimination. And the relation to elapsed time and binary discrimination in special relativity has been obscured by the focus on paths rather than areas. The chessboard model is very compelling to look at the paths, which are these, chessboard moves. But in actual fact, they represent areas. They're segments of light cones. And when you see that, you begin to see the significant. Okay. Other consequences. In this model, the smoothness of the wave function is statistical in origin. We started out with a binary four-state process, and in order to get to what looks like wave functions, we took a limit in which we put a stochastic component. Here, the collapse appears virtual in the sense that as soon as you send a clock through two slits, it's actually special relativity that says, you can land there or you can't land there. And since there's a binary process involved, it's just plus or minus, the actual particle in a sense senses a relativistic field. So it's more like the de Broglie-Bohm picture than for example the Copenhagen picture. Here, the uncertainty principle is real. It's physical. When you think of the Fourier uncertainty principle, you realize, well, okay, that's a mathematical theorem. But how does it get into the physical realm such that electrons know about it? Well, the way it gets in is simply with each particle we're saying there's a signal. We may not see it, but there is a signal that is actually the particle's clock, that it can, in a sense, for the particle, measure time evolution. As soon as that's there, then the uncertainty principle is part of that signal. So it's part of the physical reality for that electric electron. Okay, so that's all that says. Okay, so what's actually new here? Well, the origin of phase is a manifestation of time dilation. It's been discussed here before, although it's not very widely known. And that causal areas between events may be used to construct the Dirac propagator. Is also known and is part of ANPA discussions, for sure. The new bit really is just the identification of this binary discrimination in terms of the equivalence of these hinged frames. So just saying, take the world line, make it discrete, give a binary distinction so that you can use that as a clock, and then see what happens. And then, so that's really the new bit that tells you that superposition is simply special relativity sorting out what clocks are allowed when you put them through a double slit. So that's, in a sense, the new bit of the puzzle. When you look at, in order for something to be observed here, these guys have got to match up. So here the hinged frames are, of course, this one and this one. And when you see this, so these guys are going to cancel, and they cancel because this is not a Lorentz transformation of this. It's not a boost. It gets the parity. So that's the new bit. And just to sort of tie this into previous work, I've written an embarrassing number of papers on the chessboard model, but Lou and Pierre wrote one, and it's still my favorite paper. Anyway, so in that paper they asked the questions, how are the signs justified on the basis of the philosophy of bit strings? Because it is, in the end, when you come down to the chessboard model, you have to ask the question, it is binary, it works beautifully, and it has all this, it has a lot of things going for it. It gives you the Dirac propagator. But the end question is, why is it plus and minus 1? And so, in this work, the justification is completely relativistic. Right? A binary choice of clock areas is a minimum requirement for a clock to keep time, and pairs of hinged clock paths terminating with opposite parity are not related by Lorentz transformations to each other, and so are inequivalent relativistically. And so you want to get rid of them from the ensemble. So if you associate opposite signs to opposite parity, it eliminates these inequivalent paths. Okay, so just another very nice statement from this rather famous paper, pointing out that I has all of these different aspects, and you see them very much in the chessboard model. So what does that do here? Well, I just flips between the four states. Right? It's an operator that just takes us between the four states. And just to sort of say where it comes up in the algebra of the problem. Right? So our version of I is just this thing, this I sigma y. And you can see in terms of the relationship between the continuum to the discrete, we can say, well, okay, we can look at EBI theta and then set theta to pi by 2. And there's the equivalent of the Euler relation here. We look at these things and say, oh yeah, well these guys are operators. And these are the operators that appear in this work. And this just says, keep going, you haven't hit an event yet. And this is where you hit an event, and it switches to the next state. And these guys are generated by a stochastic process, right? The original model was just before state, before we put in stochastics and went for the continuum. All we had were these two guys. It takes the stochastic process to bring in those two. So there's the continuum to the discrete.
Can you leave that slide for a moment? I want to comment.
Yeah.
That the matrix for I
Yeah.
is a permutation matrix combined with a -1, 1. And the -1, 1, if you think about it all alone, is the clock. It's going -1, -1, +1, -1, +1. But then the permutation is a little shift, a little temporal shift. And the I is combining both of them together,
Yes.
making it the sort of central element in relation to the binary clock.
Absolutely. Absolutely. That's what it is. It's the central ticking mechanism for the clock. So this nice feature. So, okay, discrete versus continuous. Quantum mechanics is largely about extracting discrete eigenvalues from the Schrodinger equation. But of course, from history, we tend to think more about continuous processes than discrete processes. And so the eigenvalues and collapse in quantum mechanics strongly suggest that there's a discrete physical world, although you can't get people to agree on this. The clock paradox starts with a discrete binary model that smooths to continuous due to statistical fluctuations, and so then the Schrodinger equation, in actual fact, when you use it, picks back out the discrete aspects. And so here, phase and superposition are consequences of an extension of the two relativity postulates to piecewise inertial frames. So all you're doing here is you're saying, take standard special relativity and apply it to a signal that's just binary and happens at the Compton frequency. And so this is what it looks like. And it is really very, very simple. Right? So we start with the Einstein's postulates, and then this thing that's sort of thrown in as an afterthought to bring you back to earlier physics. You put in the world line. Well, if the world line is scale invariant, which is, the classical world line it is, it's just the particle's there and it persists in time, then you end up with special relativity. If you put in a binary clock, then
The question time.
Great. So put in the binary clock, that makes the world line, or attaches to the world line, a signal. And that, from this perspective, brings in everything. It brings in the extra element that you need that replaces the PDFs with something else, which we call a wave function, and which, in actual fact, subtracts out paths that they're not Lorentz images of each other. Okay, so that's the talk.
Any questions? Lose a question. Thanks, Don.
So is this a correct summary that are you saying that the mechanism by which we see that the Feynman chessboard solution is relativistically invariant goes over to the properties of the Schrodinger equation, even though the Schrodinger equation itself is not relativistic?
Absolutely, right.
That's what you're saying.
Yeah. That's what it is. I mean,
That's really interesting.
What I really wanted to talk about and say was basically quantum mechanics is a special relativistic effect. That if you don't have special relativity, you don't have quantum mechanics. You don't see that in the Schrodinger equation, in a sense, for the same reason that you don't see relativistic mechanics in Newtonian mechanics. You don't see the letter C and you think it all works, right? But in actual fact, we know that Newtonian mechanics arises actually from relativistic mechanics, and the C drops out in the non-relativistic expansion. The one difference with the Schrodinger equation from the relativistic equation is that the C drops out except in the phase. when you look at that phase, that little picture we showed, you look at the phase that you get from a binary particle just going along at the constant wavelength. You project it onto space at fixed t, and you see, oh, yeah, well, the binary phase knows all about the non-relativistic phase. So that part is there, and then the question is, well, if that part is there from special relativity, what about the rest of the stuff? And what about the superposition principle? And the superposition principle, when you go through this, you can see, oh, it just comes from getting rid of the stuff that isn't relativistically correct for a signal that's binary. If there's no signal, if it's just a constant function, as in the normal waterline, you don't see it. It's not an issue. But as soon as you put in that binary signal, you see it. And that gives you the phase and superposition principle. Yeah?
Do you distinguish between superposition and entanglement, or would you say entanglement is a precursor to superposition?
I guess my expectation is that entanglement is a function of the superposition. I haven't actually got any farther than the free particle. That's as far as I get, just to see where this stuff comes from. And it just seems to me that entanglement will do the same sort of thing, in the sense that what you do, you've got to look at the detector and say, okay, all the powers that come in here, they've got to be images, Lorentz images of the same thing. If they're not the same particle, they're not the same object. So I sort of expect that entanglement works the same way. Yeah? But Tony?
I'm interested in the big numbers that come up, and which this association was founded on big numbers. But I had an inspiration, I call it that. You know the p squared plus q squared energy relation, where p and q are momentum and corresponding position. And I have always been fascinated by the mathematics of that. If you say oh dear, I can't get the words out. If you say alpha q squared beta plus betas p squared, and you let out either alpha or beta shrink to zero, but not all the way to zero, you get either q squared is discrete, or the energy is discrete, but it's mostly Q squared, or the energy is mostly P squared. And I thought that what I would this is an other end of the telescope. I want to make the whole universe discrete. And this what I've suggested is a way of making the universe discrete. Because as you know, it's elementary physics. The energy of the oscillator, which is represented by P and Q, is discrete. But if it's mostly Q, it's discrete space, and it's mostly P, it's discrete momentum.
But you would think that they're both in the end discrete. I mean, you see the discreteness.
Yes.
Yeah. Well, here the analog of that here is yes. I mean, here the clock itself is discrete, right? And the reason we come up with the Schrödinger equation and the Dirac equation is simply because if you the way the thing is just set up, if you smear it at all with, for example, the Poisson distribution does it very quickly and very nicely. It just it makes everything continuous, and so you have a continuous wave function that evolves continuously in time, even though the space is just this.
So clocks, by their nature, are discrete, and if you say a particle is associated with a clock, which you do in discussions of relativity, you can't think of a clock that isn't discrete.
Well, I have to say, at this point, it is hard for me to think of an indiscrete clock, shall we say. The discrete one works so well, and you can see where the continuum one comes from, but it is an ensemble average. And so, as you say, it's not fundamentally it's discrete, but you can map it onto real functions, so you can deal with it. And this stuff is hidden. Right? And you look at the Schrödinger equation and you say, where's special relativity? Isn't it there? You don't see any discreteness in the propagation. But of course, if you do this thing, you back up and say, four-state model, it's a clock, it does this. That's how it keeps time. Then you see all this stuff, and you begin to see, oh well, space-time itself, the concept of space-time, is actually outsourcing a timekeeping to this thing called space-time, when in actual fact, if you insource it and just say it's associated with matter itself, it's there, and it gives you one. It gives you a superposition principle, or seems to.
Does it help if I quote a continuous clock
i.e. a candle.
So is it like I didn't hear the first one.
I was just thinking of an example of a continuous clock, a candle,
Oh, what?
a marked candle. You mark divisions on the candle, and as it burns down, so the passage of time is
Oh, it looks to me,
Yes,
Yeah,
but you need to mark
That's
the
a-
divisions.
Graham is this week.
yeah.
You zoom in closely enough and you see one photon at a time.
Sure. Yeah.
So whilst we're on the subject of clocks,
Oh, sorry, the clock, yeah.
may I suggest that we call a break there and reconvene at 4 o'clock and thank Garnet once again for a very